Let's take a look at some properties of vector operations. We're also going to, in this video, define the idea of linear combinations of vectors. So even though these vector operations, addition and scalar multiplication, are new, they do hold some familiar properties. We could and will look at some proofs of some of these things in this course, but for now, we'll just kind of give these properties, and hopefully with kind of how we've defined things and the geometry, they are somewhat intuitive. So the first one is commutativity of vector addition. So if we have these two vectors u and v, then u plus v is the same thing as v plus u. And then the next one we're going to look at is distributivity. So this is if we look at scalar multiplication and in combination with vector addition. So if we look at a scalar multiple a times the vector u plus v, that's equal to a times u plus a times v. So in a sense, we can distribute this scalar multiplication into this addition. And again, both of these properties might look fairly familiar. You might say, oh, yeah, of course we can do those things. But I do want to be careful with thinking that, everything we are used to and comfortable with when it comes to regular numbers is still going to hold for vectors. Next, I want to define the concept of linear combinations. So this is going to be a concept that will be really, really important for us throughout most of the course. It looks super complicated, but we're going to see some examples and hopefully convince you it's not so bad. So the definition here, the linear combination of the vectors v1, v2 up through vn with scalars c1, c2 up through cn is the vector c1 times v1 plus c2 times v2 plus up through cn times vn. The scalars c1 through cn are called the weights of the linear combination. So the idea here basically is, we can take a bunch of vectors, and a linear combination of them would just be, a combination of them in a way where what we're allowed to do is multiply them each by a scalar and add them together. And those scalars can be anything we want. So they could be positive numbers, negative numbers, zero, fractions, and they can all obviously be different numbers. So this sort of idea of a linear combination is to take a bunch of vectors and then essentially apply the two operations that we are allowed to apply to vectors, at least so far, which are, again, this idea of scalar multiplication and addition. So let's take a look at some examples that we might encounter when it comes to linear combinations. So here's a question. Is the vector 1, 5 a linear combination of the vectors 2, 1 and 3, negative 3? So in other words, is 1, 5 the result of taking each of these vectors 2, 1 and putting them together as we were talking about earlier as a linear combination? So can we find these weights? Can we find C1 and C2 such that C1 times 2, 1 plus C2 times 3, negative 3 equals 1, 5? So that's the question we are trying to answer. So can we find C1 and C2 such that C1 times 2, 1 plus C2 times 3, negative 3 equals 1, 5? And if we were to sort of start putting these together, just assuming this was possible, what would that mean? It would mean that, I guess, with scalar multiplication of to begin with, that would mean that the vector 2c1 c1 plus 3c2 negative 3c2 would equal the vector 1, 5. But now with vector addition, that would mean that the vector 2c1 plus 3c2 and c1 minus 3c2 would equal the vector 1, 5. But how can two vectors be equal? Well, two vectors are only going to be equal if their components are equal. So this basically implies that 2c1 plus 3c2 equals 1, and c1 minus 3c2 equals 5. So what we actually end up getting here is a system of equations that we would like to solve for the variables C1 and C2. And we've learned already in this course how to solve a system of equations. In particular, we've learned how to create the kind of augmented matrix and we have our algorithm for row reducing that and looking for solutions. So let's, go ahead and try and do that. So the augmented matrix for this thing would look like 2, 1, 3, minus 3, vertical line here, and then 1, 5. So that is the matrix we would like to row reduce in order to try and find a solution to this system, which would then, basically answer this question for us. Is there a linear combination? So let's just give ourselves a little bit of space here. And just erase all this stuff and we'll start fresh over here. So again, our augmented matrix looks like this. 2, 1, 3, minus 3, 1, 5. And so now let's row reduce that. We might begin actually by interchanging our two rows to get a 1 in this position here. Okay, and now we can do an R2 minus a 2R1. So we'd get a 0, 2 minus 2 is 0, and then 3 plus 6 is, 3 plus 6 is 9, and then 1 minus 10 is negative 9. So at this point, we could actually go for a solution. Actually, at this point, if all we cared about was the answer, the yes or no answer to this question, is this vector a linear combination? We should be able to say, yes, this is a linear combination, because at this point we can maybe tell, and again, if you haven't practiced enough of these row reductions, you might not be able to tell quite yet. But as you practice more, you'd be able to tell at this point that, hey, this system is consistent. There is a solution, and therefore, this vector is a linear combination of these two vectors. But let's keep going beyond that. If we know we have a linear combination, maybe we could actually sort of determine those weights, which is often something we also want to do. So I'll remind you, these are the columns kind of corresponding to the variables C1 and C2. So our second row right now says that 9C2 equals negative 9, which tells us that C2 equals negative 1. And then our first row says that C1 minus 3C2 equals 5. We can substitute in that negative 1 for C2. We'd get C1 plus 3 minus 3 times negative 1. So plus 3 equals 5, and therefore C1 equals 2. So not only does this sort of tell us, yes, we do have a linear combination, but we in particular know the weights. And we can go back and check this, right? So just up here, let's see. So 2 times 2, 1 plus, or maybe I'd say minus, because it's negative 1, 3, negative 3. And we can just go through the math. This first vector would be a 4, and a 4 minus a 3 is a 1. And then we'd have a 2 minus a negative 3, which is a 2 plus 3, which is a 5. And that is exactly what we were looking for. Let's look at another example. So again, we have, is the vector 1, 2 in this case a linear combination of 1, 1 and 2, 2? So we're looking for C1 and C2 such that C1 times 1, 1 plus C2 times 2, 2 equals 1, 2. So can we find a C1 and a C2 so that this happens. I'm not going to go through all the steps, but we could, again, sort of show that this would lead to a system where the variables are C1 and C2, and the augmented matrix would just look like this, 1, 1, 2, 2, 1, 2. And then, we can row reduce this. So we do a row 2 minus a row 1. And we get 1 minus 1 is 0, 2 minus 2 is 0, 2 minus 1 is 1. And this row now at the bottom tells us that we have an inconsistent system, right? This reduced row echelon form has a pivot in the final column. So we saw in a previous video that tells us that this has no solution, or we might just remember that, basically what this last row tells us is that 0 equals 1, which is not true. So the answer here is no, and that's basically all we would want to do for this kind of a thing. The last thing I want to do here is consider sort of the geometry of this idea of a linear combination. So here's another question. Consider the vectors u and v given in the figure below. Determine if b can be written as a linear combination of u and v. If so, determine the weights. If not, explain how you can tell. So, again, the idea would be to try and determine, can b be written as a linear combination of u and v? So are there these weights, C1 and C2, such that b equals C1 times u plus C2 times v? And, geometrically, you might just kind of visually try to look at this. Now, there's a sort of specific grid that is being drawn on this picture to help you out. Namely, you could see that the grid lines are not our standard kind of grid lines we might see parallel to the x and y axis. Instead, they are actually parallel to the vectors u and v, and they are spaced so that they are, each a distance of either u or v from the previous line, depending on the direction. And so what we can hopefully determine from this is that, if we travel up by the vector u and then kind of down, to v, then we end up at b. So the intention here was for you to recognize that this vector that I just drew here is actually negative to v. And hopefully you can tell that, right? It's taking the vector, taking the vector v, moving in the opposite direction of it, and the length being doubled here. So maybe that's a nicer picture of it there. You could see sort of how that became. So the answer to this question would be, yes, the vector b can be written as a linear combination of u and v, and in particular, b equals u minus 2 times v.